I think it's set to HDMI. Is there something that needs to be changed for that? Thank you. All right, let's get started. So today we're going to talk about inverse reinforcement learning. But before we get into that, a few logistical notes. So the project proposals are due at 11:59 p.m. tonight, so make sure to get your project proposal written up and submitted. Only one proposal is necessary per group, but every group should turn in a project proposal. And also, if it's a group proposal, make sure that you clearly indicate in your submission email who the members of the group are so that we can make sure that we give everybody a grade for that. And then more instructions are in the final project assignment that was posted on Piazza a while back. Homework 4 is due next week, and that's the last homework, so after that you'll just have the project left. Please do be sure to check the calendar on the course website. There's a milestone report that's about halfway through the remaining time in the semester, so there'll be a milestone report and then the final project report, and that's it. After that, there's no other work, and the semester is over. So today's lecture. So far, we've talked about reinforcement learning settings where we manually design a reward function to define a task. And we haven't really talked very much about where these reward functions come from, other than that they're meticulously hand-engineered and provided as sort of part of the problem formulation. So today what we're going to talk about is a different setting where we perhaps might actually want to learn the reward function from observing an expert. So if you don't know exactly what the goal of the task is, maybe you can watch somebody who does know what the goal of the task is, attempt to do that task, figure out what it is they're trying to do, and then set that as your reward function and use reinforcement learning to optimize it. So that's the setup that we'll discuss today. We're going to apply the approximate optimality model that we covered last week, this connection between inference and control. But now, instead of using it to devise better forward reinforcement learning algorithms, we'll actually use it to devise a model of the expert's behavior that will allow us to recover the reward function in a way that is reasonably robust to noise and suboptimality in the demonstrations. So the goals for today's lecture will be to understand the inverse reinforcement learning problem definition, understand how probabilistic models of behavior, like the ones that we covered last week, can be used to derive inverse reinforcement learning algorithms, and understand a few practical inverse reinforcement learning algorithms that we can actually use, from exact algorithms based on dynamic programming to practical approximate algorithms based on sampling that we can use in high-dimensional spaces and with complex neural network function approximation. All right, so before I get into the algorithm side of it, let me set up the problem a little bit with a bit of motivation. So when we have reinforcement learning problems that we want to solve, where does the reward function actually come from? So in some settings, like if you're, for example, learning to play a game, sometimes the reward function is a very natural part of the problem formulation. So if you want to win at a board game or a video game, maybe there's a score or some kind of counter that tells you how well you're doing, and that's intrinsic to the task definition. So there's a very natural source of a reward signal that you can just plug into your reinforcement learning algorithm and use that to learn. But in many real-world settings, this is not quite so simple. So there are a few reasons why it might not be so simple. There are actually slightly different reasons, different reasons in different domains. So here are a few examples. Let's say that you have a robotic task where you kind of know what you want the robot to do, but evaluating whether it's done it is very hard. So, for example, if you have a robot that needs to pour a glass of water, right? The child in this video is clearly very proficient at this, but if you want to get an autonomous machine to do it, the physical act of actually pouring the liquid into the cup might not be all that hard, but the perception problem in identifying whether the liquid has been poured into the cup successfully, and I guess the robot has to drink it afterwards, whether it was poured into the cup successfully, the perception problem there might actually be very difficult. So there are settings, actually quite a few real-world settings, where just understanding that you've done the task is itself a challenging perception problem. So it might be quite onerous to request that somebody hand-engineer a reward evaluation function for you in those settings. There are other settings where understanding the objective of the task actually requires a very in-depth understanding, for instance, of human interactions or other phenomena that are difficult to model analytically. So if you want a dialogue system to engage in conversation with human users, maybe this is an automated tech support system, Now, there might be some end goal that you want to achieve. Maybe you want, if it's a tech support system, you want to make sure that it actually helped the user fix their computer. But there's also some intangible elements like, was the user satisfied with the interaction? Were they frustrated? They have to repeat themselves many times. These sorts of factors that might be actually quite difficult to obtain ground truth measurements of. And then, of course, there are scenarios that are so filled with a kind of unwritten convention that writing down precise reward functions, even though it might be possible, for example, for autonomous driving, you can write down what the rules of the road are. There's so many kind of conventions and standards that are unwritten that people understand implicitly that it might be very difficult to obtain like a true ground truth reward function. So if you're driving a car, yeah, you need to obey the law, but there's also some common sense things that we all understand as far as what makes for a polite driver that are a little bit more intangible and perhaps harder to encode in a manually programmed reward function. So in all these scenarios, what they all have in common is that it is comparatively easy to get a person to show you one of these things being done, but quite challenging to manually program a very good reward function such that a good reinforcement learning algorithm will actually acquire that skill to the degree of proficiency that's suitable for the real world. So in these settings, the reward function is a bit hard to obtain, and in practice, if we do want to use a hand-engineered reward function, we'll sort of hack together our best guess at a proxy reward function. We'll sort of take our best attempt, we'll say, well, maybe for the dialogue, we have some sort of like user feedback at the end. Someone says, were you satisfied or dissatisfied? Maybe something like that will be your reward. But it's just a proxy to what you really want. So frequently in these settings, it's easier to provide expert demonstrations, and inverse reinforcement learning deals with the problem of figuring out what the goal is from observing an expert doing the skill. So why should we think about learning the reward function? Well, there is an alternative, and we learn about that very early on in this class, which is to just look at an expert demonstration and try to directly copy that demonstration, which is a very reasonable alternative if you have demonstration behavior. But in some cases, it can be a lot better to actually recover the expert's true objective. So if you have demonstrations and you want to do behavior cloning, imitation learning, like what we did in homework 1, you're essentially asking the system to copy, to ape the expert's motions or actions without really understanding the underlying cause of those motions or actions. So in some cases that might work well, especially if you have a lot of data and minimal domain shift, but it's not necessarily the most generalizable representation of the task. It doesn't necessarily capture the salient parts of the behavior. So if you're trying to blindly mimic the expert, you'll mimic every aspect of what the expert did, whether it was important to the task or not, which means that when you make mistakes, and any learning system will make mistakes, those mistakes are not necessarily the ones that are sort of least harmful for the final task performance because you haven't understood the objective of the task. And of course, in some cases, the expert might have different capabilities. So if you're trying to learn to pour a glass of water and you're a robot with maybe a different actuator, if you understand the real goal of the water pouring task, then you can carry out that task in the way that is most optimal for your own embodiment, which may not be the same as what was optimal for the expert. So if you figure out the goal of the task, you can then transfer that task to new settings, new domains, and new capabilities more easily. So if we can reason about what the expert is trying to achieve instead, then we can perhaps do a better job of generalization, capture the aspects of the task that are most salient, and also be able to transfer to things like different capabilities in different domains. And this is something that people actually do very naturally. So this is a video that I think I showed earlier on in the course, but I want to show it here again. This is an experiment with toddlers where this is studying their ability to understand a person's intent. So this, the child here is, whoops, sorry. The child here is watching this, the experimenter attempting to do something, and all of you have probably guessed what it is that he's trying to do. And the child is going to watch this guy for a little bit, and then he's going to figure out what is the purpose of this behavior. And of course, the child's reaction is not to blindly mimic what the experimenter is doing, but to actually do something completely different that he knows will actually assist in this task. So it's not an imitation problem, it's really an intent inference problem. And here, similar idea. So he's watching this guy putting something on a clothes rack, and he drops the this thing here, and the child is going to go and help him out. And this is also, an instance of different capabilities, right? The child here can't even reach the clothesline, but he knows that if he hands that thing to the guy, then he'll succeed at the task. All right, so this problem of inferring reward functions from demonstration is called inverse reinforcement learning. It's also sometimes called inverse optimal control. So if you see inverse optimal control, that's referring to the same problem. And we can define the problem like this. We can say that just like in reinforcement learning, you get a state space and an action space. But now you're going to get samples from the optimal policy or from a near optimal policy, so this pi star. And sometimes you'll also assume that you know the dynamics model. So we'll actually talk in this lecture about IRL algorithms that assume knowledge of the dynamics model and also IRL algorithms that do not assume knowledge of the dynamics model, so both model-based and model-free methods. And the goal is to recover the reward function. And typically, the reason that we want to recover the reward function is so that we can then optimize that reward function to get a policy. And this policy will hopefully be better at doing the task than if we had just directly behavior cloned the expert demonstrations. Now, there are a number of challenges with inverse reinforcement learning, some of them actually very fundamental. One of the really big challenges is that inverse reinforcement learning, especially if you frame the problem a little bit carelessly, can be very badly underdefined. So when we see the video on the previous slide with the child helping the experimenter carry out these tasks, we have a lot of prior knowledge about how that world works. We understand that, you know, if you can open the doors to a closet and you can put the books in there. You know that if you have one of those clothespins, you can use it to pin the cloth to the clothesline. This is all stuff that we already knew in advance. We didn't figure that out from watching the video, and neither did the child. This is knowledge that we have as a consequence of our past life experiences. If you're thinking about a machine learning algorithm trying to figure out one of these problems, you have to remember that it starts off knowing essentially nothing. So if we want to sort of imagine what an IRL problem would look like to a computer, we should, you know, maybe start with something that's a little bit abstract where our prior knowledge doesn't necessarily give us a lot of guidance. So here's a little abstract world that is populated by triangles and circles. And imagine that I show you, oh, this triangle starts off in the middle and then it moves to the right. Okay, this is the triangle's behavior. And then when I say, well, why did it do that? Is it that it likes purple things? Is it that it likes going to the right? Is it that you know, it had some velocity and it was rolling to the right? Like, what is the underlying cause for its behavior? And the fact is that we can't figure it out. In this abstract environment, if we're not allowed to use any kind of prior knowledge that we have, there's ambiguity. Maybe it moved to the right because it likes moving to the right. Maybe it moved to the right because it likes purple things. Maybe it's because it hates red things. All of these are actually reasonable explanations that could all explain exactly the same behavior. And we can turn this actually into a formal statement that for any observed policy, in general, there's an infinite set of reward functions that will all make that policy appear optimal. So unless we introduce some additional machinery, which we will in a second, the IRL problem is actually underdefined, meaning that there isn't a single right answer. And there's nothing in the problem to disambiguate multiple right answers. Yes?
But having more like data examples would let you eliminate a lot of those hypotheses, right? If you say like this moved to right because it hates the red, but in another scenario where there is a red, it didn't go to right, then it can help you eliminate some.
Yes, although in general, you actually, with the definition as written on the slide, you actually can't eliminate all ambiguity no matter how much data you have. And one of the ways you can think about it is that you can always construct a reward function that just says, in every state that you saw, the action that the expert did has a reward of like plus 1,000,000, and everything else is minus 1,000,000. And that's a perfectly good explanation. So yes, more data does help, but up to a point. The other problem is that it's actually quite difficult to evaluate a learned reward. And by difficult, I mean difficult computationally. So typically, IRL algorithms will have this structure where they attempt to improve the reward function. And then to evaluate how good that reward function is, or to compute its gradient or something like that, they need to actually solve the corresponding forward reinforcement learning problem. So some of the algorithms that we'll discuss sort of have this flavor where actually they're doing reinforcement learning in the inner loop of an inverse reinforcement learning procedure. Because every time you've improved your reward function, in order to figure out how to improve it next, you need to basically see how the corresponding policy differs from the expert's policy. So that can be very demanding computationally or in terms of samples. And the last problem is that even if you can overcome the first two, the demonstrations that you actually got from the expert, especially if it's a human expert, are unlikely to actually be perfectly optimal with respect to any reward function. And this is what we discussed last week with the suboptimal monkeys, that you know, humans, animals, and any kind of practical expert from which you might get demonstrations are probably not actually perfectly optimal with respect to any reward function. They might be approximately optimal. Okay, so that's the circle moving. Okay, let's write this down a little bit more formally, the problem definition. So, and what I'll do here is I'll actually show you two columns just to compare. On the left is forward reinforcement learning, on the right is inverse reinforcement learning. So both of them are given states and actions, states from some set of states, actions from some set of actions. Both of them are sometimes given transition dynamics, or you learn the transition dynamics, or you might have a model-free algorithm that doesn't require them, so that's the same in both cases. For forward reinforcement learning, you're given a reward function, and you're tasked with learning the optimal policy pi star. In inverse reinforcement learning, you get samples that are sampled from an optimal or approximately optimal policy pi star, and then you're tasked with learning a reward function, which now I'm going to denote as r psi, where psi is the reward parameters. Because I already used theta for policy parameters, phi for value function parameters, so I'll use psi for the reward parameters. And you can represent reward functions for IRL in a number of different ways. They need to have some free parameters. A very popular choice in some of the classic IRL work is to use linear reward functions, where you say that the size are actually weights on a set of features. So the intuition here is that all the features are things that you either want or don't want. And the weight on that feature, psi I, tells you how much you do or do not want that thing. You can also devise deep inverse reinforcement learning algorithms where the reward function is a nonlinear function of the states and actions, in which case the psi will be the parameters or the weights of that neural net. So I'll talk first a bit about linear reward functions, and then towards the end of the lecture I'll also discuss how we can do nonlinear neural network reward functions. So first, let's discuss a, oh yeah, and of course once you learn it, you use it to then learn the optimal policy. There's a question back there?
Yes. Do you assume that you have full insight into the agent's observations, or is it from the perspective of, I have godlike perspective and I can see what you actually did versus...
So for all of the algorithms that I'll discuss here, the assumption is that you have access to exactly the states and actions that the expert had. We'll actually have a lecture on advanced imitation learning later in the course where we'll discuss the setting that you just mentioned, but for now we assume that we see exactly the same stuff that the experts saw. Yeah. Okay, so before I get into the main kind of algorithmic topic of today's lecture, I want to present a little bit of background. So I'll talk a little bit about these feature matching inverse reinforcement learning algorithms. I have just 2 slides on that. And I want to mention, these are not algorithms that we'll cover in a lot of detail, but I want to mention them because these are actually some of the earlier IRL algorithms, and this is kind of to provide a little bit of background knowledge on this topic. So, you know, inverse reinforcement learning is a relatively young field. Some of the earliest work appeared around 2000. And early on, the way that people generally thought about inverse reinforcement learning problems was something like this. You would write down a linear reward function, and as I mentioned, the meaning of this is that all the f's are things you either want or don't want, and the psi tells you how much you do or do not want each of them. And then you might say, well, what makes a policy that behaves similarly to the expert? Well, if the f's are the things that you really care about, maybe a reasonable thing to do is to say, well, what if you match the expectations of f's? So if the expected values of the f's for the learn policy are the same as the expected values of the f's for the expert policy, then we've sort of matched the relevant parts of the behavior. So if we let pi superscript r psi be the optimal policy for r psi, so this is the policy that you get if you optimize r psi, then we can write down this expected feature matching as following. We can pose the problem as one of picking psi such that the expected value of FSA under pi r psi is equal to the expected value of FSA under pi star. The expected value of the features under pi r psi that you can get by computing the state action marginal, or equivalently by just running pi psi and measuring the feature expectation. So you can sample from that policy, see which trajectories you get, and just average together the features of those trajectories. And the expected features under the optimal policy, those you get from your data. So the optimal policy is, of course, unknown, but you can approximate expectations under the unknown optimal policy by using the expert demonstrations, which you assume to be samples from that unknown optimal policy. So the way that you would get this is just by averaging together the feature values along all of your demonstrations. And the way that you would get this is by averaging together the feature values along all the trajectories that you drew from the policy pi r psi, which you got by optimizing your learned reward r psi. And then you would somehow have to compute a gradient of this thing and try to improve it. Now, this formulation is actually still ambiguous. So you can match the feature expectations and have completely different values of psi. So there's still ambiguity in what makes for a good reward function, and all this stuff with the triangle still applies. So after thinking about this for a little while, one of the things that, that people kind of decided on was that, well, this kind of problem of ambiguity in regard to the weights looks an awful lot like the problem with ambiguity in regard to the weights of a linear classifier. And one of the ways that you can resolve that is by borrowing an idea from support vector machines. You can say, well, let's try to build a maximum margin reward function. So there's actually quite a bit of work on formulating inverse reinforcement learning as margin maximization problems. So if we want to write down a margin maximization problem in IRL, we can start by doing something like this. We can say, let's maximize the value of some scalar valued margin m such that the reward of the expert's policy, pi star, and remember, the reward is linear in size, so you can just compute the expectations of the features and then dot product them with psi, and you get the expected reward. This reward is greater than or equal to the reward of the best policy you can find in your policy class plus a margin. And you want to maximize that margin. So this is the primal form of the margin maximization problem. No one actually ever solves the primal form, but we can write it out like this. This is a little messed up if you write this out for IRL, for the reason that these pi's, your pi star might actually be in the set capital pi, so this might actually just be impossible. The margin might always be 0. So this by itself is very unsatisfying. You need to somehow weight this right side of this inequality by the similarity between pi star and pi. So you want to say, well, I want to maximize the margin, but it's much more important to maximize the margin against policies that look different from the expert's policy pi star. So you want to find a reward function under which the expert's policy looks better than all the other policies, but only better than the policies that are actually different from the expert, because obviously there's going to be some policy that is exactly the expert's policy, and it's going to have exactly the same reward. So one of the ways that we can do this is we can recall the trick that we use in SVMs, where we rewrite the margin maximization problem as the problem of minimizing the squared the magnitude of the weights, and then we replace the m here by 1. So this is the same exact thing that we do in an SVM. And now it's a lot easier to bring in this notion of similarity. We can just say this 1 is going to become a measure of distance between pi and pi star. So we say we want to the expert's policy, we want its reward to be greater than or equal to the reward of the best policy with respect to the reward, plus some discrepancy measure that measures how different that policy is from pi star. And one very reasonable thing to use here is the difference of the feature expectations. So you want to say, I want to find a reward under which the margin is maximized against all the other policies, but maximize it even more for policies that have different feature counts. So if you have a policy with the same exact feature count as the expert, don't worry about that margin. But if you have a policy with a very different feature count, it should look a lot worse under your learned reward than the expert's policy. OK. Does anybody have any questions about this formulation of the IRL problem? Yes?
So here we take this f as a vector, I think. So it's
yes.
a different component. But from f and a to different component of f, it seems there should be a function relationship. But so there should be some weight or something like that inside. Those kind of the parameters, where do they come from?
Well, so the weights are right here. So f is a vector of features. You can imagine, let's say that you're doing a driving task. F of SA might be a vector with a number of entries where one entry is, are you currently in a collision with another vehicle? Another entry is, how far are you away from the center of the lane? Another entry might be, how fast are you going? And then you might say, well, I want to not collide, I want to be in the center of the lane, I want to go really, really fast. So you say, -1 for the first feature to not collide, -1 for the second feature to be in the middle of the lane, and plus 1 million for the last feature because I really want to go super fast. So that's kind of the intuition behind what these mean. Any other questions? OK. So this kind of margin-based formulation is actually going to resolve the ambiguity issue in inverse reinforcement learning, because it's going to say, well, the way that you disambiguate between two equally good rewards is you pick the one under which the policies that don't match the feature counts have a larger margin against the policies that do, especially the optimal policy. So this margin maximization does, in fact, resolve the ambiguity, but it has a number of issues. First, it resolves the ambiguity in kind of a weird way. Like, you know, these rewards, they don't really have any meaningful units here. So, okay, you can resolve the ambiguity, but why? Why is this the right way to do it? Why is giving a bigger margin going to give you a better reward? It's a bit arbitrary. There's not really any clear model of expert suboptimality. So usually in an SVM, the way that you deal with settings where the classes are not perfectly separable is that you add slack variables. And you can add slack variables to the margin-based IRL formulation as well. You can basically put a slack variable over here on this side and then minimize the slack variables, which is something people have done. But again, it's a little bit of an arbitrary model of expert suboptimality. It just says, yeah, the expert can be suboptimal, and I don't have any explanation for why, so I'll just put in some slack variables. It fixes the problem to some degree, but it doesn't provide a very satisfying explanation and can have not such great performance with real human data. And this is kind of a messy constraint optimization problem, which is particularly relevant for us because if we eventually want to scale beyond linear reward functions, we need to be able to handle complex nonlinear reward functions like neural nets. Having a complicated constraint optimization problem is kind of problematic because we'd like to use nice, efficient, scalable stochastic gradient descent methods in the end. So I'll actually not discuss this further. I'll talk about a different way of doing IRL for the remainder of this lecture. But if you're interested in margin-based IRL methods and want to read more about them, here is a few suggested readings. So there's apprenticeship learning via inverse reinforcement learning. This is one of the classic papers in this field from 2004. And then a more modernized algorithm that is actually quite good to use in practice is called maximum margin planning by Ratliff et al. So if you're interested in margin-based IRL, I would recommend checking out those papers. Okay, so this is kind of, this class of IRL methods has its origins in some classical machine learning methods like SVMs. But another way that we can attack the inverse reinforcement learning problem is that we can think about it as a modeling problem, a problem of modeling human behavior. If we can construct a good model for human behavior, we can then fit that model to the human data and use that to recover a reward function. And this is what we discussed a little bit last week. So we talked about how, for example, we can construct models of human behavior by starting from the assumption that the human is being optimal, figure out what is the sequence of actions that they might do for a given reward function, and so on. So this is the slide from last week about how we can use the principle of optimality to try to explain human behavior. And one of the things we talked about last week is that, of course, real human and animal behavior doesn't perfectly satisfy this principle, that there's always a little bit of suboptimality in the way that real humans and animals behave. And the way that we tackled this last week was by introducing a probabilistic graphical model of decision-making, where we said, let's not worry about this hard optimality notion that we had before, where we're perfectly maximizing reward, but instead let's draw a graphical model such that inference in this graphical model corresponds to decision-making. So we'll have some distribution over trajectories. We'll introduce these optimality variables O, and we'll say that the optimality variables O, their probability of being on is proportional to the exponential of the reward. And then we saw that if we follow this line of reasoning, we arrive at this nice conclusion that the probability of seeing a trajectory is proportional to the probability of that trajectory occurring due to physics times the exponential of its reward. So the most rewarding trajectory is the most likely, and trajectories get exponentially less likely as their reward decreases. So last week we talked about how we can use this model to solve for policies and state distributions. And today we're going to talk about how we can do learning in this model to actually acquire the reward function given some data that is assumed to come from this model. So our goal in inverse reinforcement learning under this graphical model view of the world is to essentially learn the distribution of the optimality variables. So now we're going to introduce psi in here. So psi parameterizes the reward. And before we had P of O given SA is proportional to the exponential of R. Now it's proportional to the exponential of R psi. And our goal is to learn psi, so which are the reward parameters. And I'll write these things out like this. I'll actually explicitly put the psi as one of the variables that we're conditioning on, just to make it explicit that now the optimality variable depends on psi. And psi is the thing that we want to learn. So that means that the probability of a trajectory, given all the optimality variables being true and psi, is proportional to this, just like before. And we have some data, we have some trajectories, tau I, which are assumed to be sampled from pi star tau, where pi star tau now is the softly optimal trajectory distribution, which is what we get by running the policy, the one that we derived last week, the P of A given S comma O. And now we can just do maximum likelihood learning. So if we have some data, we have a graphical model, how do we learn the parameters? We maximize the log probability of the data. So we can write out that maximization problem, just maximize with respect to psi, 1 over n times the sum over all of our sample trajectories of the log probabilities of those trajectories given O1 through t and psi. So this is just a standard, familiar maximum likelihood learning problem. And we're going to derive how we can solve this learning problem. So first, let's substitute in the log p of tau given O and psi. Now, you'll note that this term, the p of tau due to the dynamics, that one doesn't depend on psi at all. So when we take the log of this, we get log p of tau plus this part, so we can just ignore the first part because psi is not going to influence it. So we can just plug in the r. So that means that the problem we're really trying to solve is maximize with respect to psi, the sum of the rewards of the trajectories minus the log normalizer. So if it wasn't for the log normalizer, this would be a very silly problem. We would just say, make the rewards of the trajectories big. A good way to do that is just make the weights gigantic. But we have this log normalizer to worry about, and that's called the partition function, and that's really the hard part. That's what makes it really complicated. So if it wasn't for the partition function, this would be a trivial problem, but the partition function is going to give us a little bit of a headache and necessitate a couple more slides of math to derive the maximum likelihood learning rule here. So let's get into that. Here's our problem, and the partition function is the thing that we need to worry about, and the partition function is given by the integral over all trajectories of the unnormalized probability, which is p of tau times the exponential of the reward of tau. And when I write out r psi of tau, that's just shorthand for the sum of the rewards over all the time steps within tau. Okay. And if your state space and action space are discrete, then this integral just becomes a sum. Now, this is a pretty crazy integral because this is an integral over all possible trajectories you could get. So that's pretty intense, and we need some way to make this tractable. So let's substitute in the z in here, and let's take the gradient with respect to psi. So the gradient of the first part, that's very easy. That's just the gradient with respect to psi of r psi. The gradient of the second part, well, log z, so the derivative of log z is 1 over z times grad z. So we get the 1 over z, and then we get the grad of this. So when we put that in, we just end up with this thing, right? So this is the equation for the gradient with respect to psi. And now something interesting that you can observe about this equation is that for this second part, this thing, the 1 over z times the integral p tau x bar tau, this is just the probability of that trajectory under your model. So the second term is just an expectation of the gradient of the reward under your current model. And that means that you can equivalently rewrite the gradient like this. It's just the difference of two expectations. The first expectation is under the data. So this is the expectation with respect to trajectory sampled from pi star, because that's where these samples come from, of the gradient of r, minus the expectation where the taus are sampled from your current model of grad r psi. So you have the expected gradient of the reward under the data minus the expected gradient of the reward under the model, which means make the data big and make the stuff from the model small. And actually, those of you that are familiar with how you train the parameters in Markov random fields will recognize this as basically the universal formula for training the parameters in Markov random fields or in general energy-based models. So you increase the log probabilities of the data and decrease the unnormalized log probabilities from the model. And that's exactly what this is doing. So that means that if we want to compute this gradient, the main thing that we have to do, the main thing that's difficult, is to evaluate the second expectation. The first expectation is easy because we just sample. We have these samples. So this is we estimate the first part with expert samples. Sorry about the annoying sliding animation. I don't know why it's happening. You estimate the first part with expert samples and estimate the second part with a little bit of inference. So this is where we're going to actually make use of the forward and backward inference that we covered in last week's lecture. So first part is easy, that's just summation. Second part is a little harder. Okay, so let's talk about that second part. That's the main thing we have to do. So one of the ways that we can decompose that second part is to actually break this trajectory into individual time steps. That's going to let us reason about tractable ways to compute this expectation. So remember that r psi tau is actually a sum over all the time steps of r psi of the state in action at that time step. So we can substitute that in there. And now you'll know that the reward at any given time step only depends on the state action marginal at that time step. So what we can do is we can actually take the sum out of the expectation, like this, and then inside the sum, we just have an expectation with respect to the state action marginal at that time step. And that's going to be a little bit more manageable. So now we've turned this second term up here into the sum over all the time steps of the expectation under the state action marginal at that time step of the gradient of the reward at that time step. And this is where we can apply some of the tools from last week. We can say that this part, this is actually just the probability of the action at that step times the probability of the state at that step, right? Because this is P of S comma A, which we can factorize as P of A given S times P of S. And where have we seen these things before? Well, we saw them last week when we discussed the forward and backward messages. And in particular, this part is the policy. And the policy, as we discussed last week, is the state action backward message divided by the state backward message. So this is when we derived how we can compute the policy under soft optimality. And the second part is the state marginal. The state marginal, as we discussed, is proportional to the product of the forward and backward message. And now we're multiplying these things together. So this thing cancels with this thing, and you just get the product of the state action backward message and the state forward message. So if we can apply the inference algorithms from last week, we can just use them to directly compute this distribution under which we're computing this expectation. In discrete state and action spaces, you can actually compute this distribution exactly. So you can actually just have a tabular representation of a frequency associated with each state action pair and actually exactly compute these messages. So this is the backward message, this is the forward message, and you can exactly represent them as a big table over your discrete states and actions in small discrete spaces. Yes?
I guess, what is the normalizing term here again?
Well, if you're doing this in a tabular setting, the way that you would do this is you would compute an unnormalized probability for every state action pair, and then you would just sum over all states and actions.
Okay.
So it's intractable to sum over all possible trajectories, but it's quite tractable in small discrete spaces to sum over all states and actions.
For a single time step?
For a single time step, exactly. Any other questions? And yes, those of you that are wondering, this is in fact intractable in large continuous spaces, and we'll address that later on in the lecture after the break. But for small and discrete spaces, it's quite feasible. OK, so now the way that we can actually derive our learning algorithm is we can define this thing called mu of S comma A, the state action marginal, as being proportional to the state action backward message times the state forward message. And then we can express this expectation as just the sum over all the time steps of the integral of mu SA times grad RSA. And in particular, you can recognize this thing as basically being an inner product. So we can equivalently write this, if we're a little scared of integrals, as a giant inner product of this vector of all state action visitation frequencies times all the grad Rs. So this vector notation here just means the gradient of the reward at all the states and actions, and this is the probability of all the states and actions. And you just take their inner product. So if you have a tabular representation, if you have a discrete state and action space, you can literally just implement this as an inner product of two big vectors. OK, so this is the state visitation probability for each S comma A, and that thing is the gradient of the reward at every state and action. So now, using this, we can actually write down the Maxent inverse reinforcement learning algorithm. And it looks like this. First, given your current psi, compute the backward messages. And this, you can look at the previous lecture on last week on Wednesday to see how those can be computed. Then compute the forward messages alpha. Then compute your state action visitation frequencies at every time step by multiplying beta and alpha. Then evaluate the gradient. And it's a big, scary equation, but all this really is the average gradient of the reward in your data minus the average gradient under your state action visitation frequencies. And that second part can be implemented as a giant inner product. And then step 5, take a gradient ascent step. to increase your log likelihood. And that's it, and then you repeat. So this is the basic form, the exact form of the tabular version of maxent IRL. These steps 1, 2, and 3, they basically amount to solving the corresponding MDP using the soft optimality principle. And that's a little bit expensive as your state and action space gets large, but if you have relatively small tabular state and action spaces, it's reasonably tractable. And in fact, this algorithm has been used in practice to learn some interesting reward functions. So before I get into that, one of the things I want to mention is why this algorithm is called maxent IRL. And the reason it's called maxent IRL, in last lecture, we talked about how when you have this principle of soft optimality, the corresponding policy optimization objective includes this entropy maximization term. And that's actually the same thing as what's happening here. So you can actually derive, in the case where you have a linear reward function, a reward function that is psi transpose times some features, that the solution you get from this is going to be the solution to this problem of maximizing the entropy of your policy subject to the constraint that the feature expectations are equal between the learned policy and the expert. So this is a maximum entropy model, and this algorithm will learn the parameters of that maximum entropy model for the inverse reinforcement learning problem. In the nonlinear case, this story gets a little bit more muddled, but in the linear case, it actually has a very direct connection to maximum entropy models. OK. So yeah, this I already discussed. So one example of work that used the maximum entropy IRL algorithm to actually solve some interesting real-world reward learning problems is this one, the maxent IRL paper by Brian Ziebart and colleagues. And what they did in this work is they applied the maxent IRL algorithm to discrete MDPs that corresponded to navigation of road networks. So they had data from human drivers, actually taxi cab drivers, navigating the city. I believe it was actually Pittsburgh. And they would look at, they basically took the street network, encoded it as an MDP, where the actions are the individual turns that you make at intersections. So it's a discrete state space and discrete action space. And it's a large discrete state and action space, but it's still quite tractable, meaning that you can have a giant table of all the possible intersections and all the possible streets. And then they could do interesting things like, for example, watch somebody driving. So this dark line is a GPS trace. And as they're driving, they can make inferences about their possible destination. So they could actually try to fit the features for different destinations based on their driving so far and try to figure out, well, how likely are they to be approaching a particular destination over any other. They also did things like devise a planning objective based on a large amount of data from human taxi cab drivers that tried to figure out what kind of road features are more or less costly. So the kind of features they used were things like, are you driving on a highway, are you driving on a local street, are you driving on a street with 3 lanes, 2 lanes, do you prefer right turns, left turns? Left turns take a little bit longer, so maybe you want to avoid those. And those were the features that they gave to their reward function. It was a linear reward function. And then they would figure out the weights on those features to try to get a navigation reward function that was a little bit more representative of how the human drivers would drive. So this is an example of how you can actually get reasonably practical real-world results, even with relatively small tabular state and action representations. Here's another more recent paper that looked at using the same algorithm, but with more complex reward representations. So in this paper, they still had a tabular state and action space, actually encoded as a grid world, but now what they did is they actually had a more expressive reward function representation. So the reward function was now represented with a neural network, and the setup was this, that they would have some sort of a discrete environment, like maybe a grid world, and later on some robotic environments where they did overhead navigation. And the same exact algorithm could be used in these environments to compute the state action visitation frequencies, but the gradient was then computed through a convolutional neural network that would actually look at some visual representation of the environment and output a reward. So one example of this is a little navigation task where you have a vehicle, it's trying to traverse some environment, and you want to build a cost map or a reward map from overhead images. So the overhead images might have they might not actually be pixel images. They might have some sort of features encoded in them, like the height of the terrain, the variability in the height, visibility, and so on. And then the actual reward function to be used for planning would be a nonlinear function of these features. And because the convolutional network can actually incorporate a little bit of spatial context. So the particular value of a point in space might depend on a little spatial context around that point. So they collected a bunch of actual demonstration data on a vehicle and then used that to train a reward function using this algorithm. So the state space here is still discrete. It's actually just a big table of 2D locations, and the action space just corresponds to moving between those locations. But the reward function now is a lot more complex. OK. So I'll stop there and take a little break. And then after the break, we'll talk about how we can extend maxent IRL to large and continuous spaces. So we'll be back in 3 minutes. All right, let's continue. So in the first half of this lecture, we talked about how we can do inverse reinforcement learning with, potentially with neural net reward functions, but on small discrete spaces where we could exactly compute these state action visitation frequencies so that we can compute the gradient. So what about larger reinforcement learning problems? So the maxent IRL framework gives us this probabilistic framework for learning reward functions. It's a nice probabilistic model. But computing the gradient requires enumerating these state action visitation frequencies, which can be intractable. So it's only really viable for small discrete state and action spaces. And it really basically amounts to this dynamic programming algorithm. So if you remember from last week, we talked about how computing those backward messages exactly looks a lot like value iteration. And in practice, using maxent on these discrete spaces also amounts to a very value iteration-like algorithm. So it's good for small spaces, doesn't really scale to large spaces or to unknown dynamics. So if we really want broadly applicable deep inverse reinforcement learning algorithms, we need to basically get two things. We need to get large and continuous state and action spaces, and we need to get effective learning under unknown dynamics. So similar to how in model-free reinforcement learning, we can get away with just sampling from the dynamical system. Here we'd like to be able to do that instead of having to exactly know the transition dynamics. So how can we do unknown dynamics and large state and action spaces? Well, we're going to sample like in standard model free RL. And to figure out how that can be enabled, let's go back to this form of the gradient. So if you remember, before we broke up this trajectory distribution into sums over states and actions, we had the expectation of the gradient under the optimal policy, which is approximated using samples from the expert, minus the expectation of the gradient on trajectories sampled from the model. So this is estimated with expert samples, and this is the soft optimal policy under the current reward. And the idea behind how we can scale deep IRL to high-dimensional spaces and unknown dynamics is that we're going to try to get this distribution here using a model-free approach. So the idea is to learn P of A given S comma O comma psi, which, as you recall from last week, is the form of the soft optimal policy, using any maxent RL algorithm, using any forward algorithm, which can also be a model-free algorithm. And then run this policy to sample trajectories from the model. And then you can approximate this gradient using the difference of two sums, a sample estimate of the expectation from the expert and a sample estimate of the expectation from the model. So here we'll actually attempt to learn this P of A given S and then sample from it to compute the gradient. So sum over expert samples and sum over policy samples. OK. Now, we could actually do this. It's a little bit expensive, though, because this step here, this learning the P of A given S comma O comma psi, especially if you don't have a dynamics model, this might actually involve running some big model-free RL algorithm, which might take hours of time if you're running in a simulator, or hours or even days of sampling if you're running on a real physical system inside the inner loop of a gradient-based optimization. So this can quickly get completely intractable. But perhaps we can take a little shortcut. Perhaps we don't actually need to optimize this P of A given S comma O comma psi all the way to convergence. Maybe we can just improve the policy a little bit and then approximately estimate the gradient. So instead of learning this, well, let's just improve it, just a little bit, and then take a gradient step. Now, the trouble now is that this sum here is no longer going to actually be an unbiased estimate of the expectation of the gradient under the model, because this P of A given S is no longer actually the best action distribution given the current psi. We're sampling from the wrong distribution. So what can we do if we're sampling from the wrong distribution? Well, we can use importance sampling. So what we can do is we can sample from some other policy that's not quite as good as the optimal policy, but maybe it's on its way to getting better. Use a sample-based estimate of the second term, but weight the different terms with importance weights to actually make them look like samples from the right distribution. So what we do is we put these weights in here, and we normalize by the sum of the weights. And what the weights are equal to is the expected reward under the current reward function divided by the probability of that trajectory from the distribution that it was drawn from. And we don't need to normalize this thing because we'll just divide by the sum of the weights. So if we use a normalized importance sampling, we don't care about the fact that this distribution is not normalized. So we'll sample from some pi, and hopefully that pi will be improving. But if it hasn't fully converged, then these importance weights will basically fix the problem for us. So if we put in these importance weights, that basically reweights the samples to make the ones that have higher reward a little bit more probable, or ones that were unlikely from the policy a little bit more probable. OK, so let's analyze this importance sampling a little bit more. The importance weights are going to look very similar to the importance weights that we saw back when we talked about importance sampling for policy gradient. So I can substitute in the trajectory probabilities in here, and you get the initial state probabilities, the transition probabilities, and at the top the exponential rewards, and at the bottom the policy probabilities. And of course, the initial states and the transition probabilities cancel out, just like they did in the policy gradients lecture, and we're just left with this ratio. So that means that we just have to evaluate these weights, we just have to evaluate the exponential of the reward of the entire trajectory divided by the product of the probabilities of all the actions that were taken along that trajectory. And we know from the lecture from last week that if pi was actually optimizing this reward, if it was actually the exact optimal policy with respect to that reward, then these two terms would also cancel and get a weight of 1. But if pi does not perfectly optimize that reward, then the terms won't cancel and we'll actually have this ratio. And that'll be our importance weight. So then, of course, a natural question to ask is, well, which sampling distribution is actually best? Like, if we could choose this pi to be anything, is it actually best to choose it to be the exponential of r? And we can study that. So in importance sampling, the optimal importance sampling distribution, meaning the distribution that minimizes the variance of the estimator, if you're trying to estimate the probability, the expectation of some function f of x under a distribution p of x, the optimal distribution is actually the absolute value of f times p. So this is a standard result in importance sampling. So if you can choose a sampling distribution like this, then you'll have the lowest variance importance sampling estimator. And so that means that up here, if we're trying to estimate the expectation of the exponential reward, then the right distribution is, in fact, the exponential of r. It's probably worth saying that if you're trying to estimate the expectation of the gradient of the reward, this is no longer true. So you can actually get an even better estimator if you put in the magnitude of the gradient in there. But the quantity that you're differentiating for that, this is the optimal distribution, which is the max net optimal policy. So that means that if you're improving your policy as you're training your reward function, then basically every step that you improve your policy with respect to r psi, you get closer and closer to the optimal distribution. And until you get there, you can use these importance weights to correct your mistakes. OK, does anybody have any question about this sampling-based method for estimating the gradient and the importance sampling correction?
So is
yes.
I guess you're saying that the distribution gets like the pi gets closer to the optimal reward. So is it a thing done where you see how if it's getting closer to 1 to see if you're converging kind of thing?
The weights, you mean?
Yeah, yeah.
Yeah, you could do that. I haven't seen that done, but yeah, in principle, as you get closer and closer to convergence, these weights should approach 1 if things are working properly. Yeah. I mean, in practice, you can usually get a decent reward function long before that happens. But yeah. All right, so one of the kind of earlier algorithms that discussed this approach with the alternating optimization of the policy and the reward function was this method called guided cost learning. The paper is actually presented as learning a cost function, but remember, the cost function is just the negative of the reward function. So mentally substitute a negative sign, and you get the same terminology as what we've been using in this class. So the idea is very simple, that you have some initial policy, which might be some random behavior, and you have a bunch of human demonstrations. And then you'll run your policy on your system, for example, on your robot, to get samples from that policy. And then you'll use importance sampling plus the human demonstrations to update your reward function using the samples and the demonstrations. And then you'll take the policy and you'll actually improve it with respect to that reward function to get a slightly better distribution to sample from next time, sample some more samples from that policy, importance weight them, update the reward function, and go around and around again. So every step of the algorithm, it updates the reward function, updates the policy, and so on. And then at the end, you get a reward function over here, and you actually get a policy over here. So by the end, you should have a policy that's pretty decent with respect to this reward function, and a reward function that is actually a good estimate of the expert's reward function. So this side here, this is, I guess the way I wrote this equation is actually backwards. So this side here is estimating this term, the importance weighted term, and these human demonstrations here are estimating this term. And every step, this part changes, but this part stays the same. Okay, so this is a practical instantiation of this approach in an algorithm that we could actually implement. In this paper, it actually used a model-based method based on guided policy search for the policy optimization, but in principle, any policy improvement step could actually be used there. All right, so I can show a few little videos of this thing in action just to give you some idea of what this looks like. So this was for a robotic application that performed a variety of little manipulation tasks. And the two tasks were stacking dishes into a rack, where these are kind of fragile and you can break them if you hit them too hard. And the other one is pouring some almonds from a cup into another cup. And here the reward function involves actually localizing the target cup by picking up on its visual features. One of the comparisons that I'll show in these videos is actually to another method that had sort of that propose kind of half of this cycle. So one of the things that was explored in these other two papers, one by Kelly Christian et al. In 2013 and one by Boularet et al. In 2011, is a version of this method that used importance sampling but did not actually use an update to the policy. So here, this is a much simpler way to do it, but has a much worse sampling distribution. The idea is that you design manually some sampling distribution Q0, and then you just use importance sampling to compute the IRL objective, which is actually a reasonable way to do it as well if you can design a decent sampling distribution here. Okay, so here's a video from this paper that shows how some of this stuff works. Here, this is just for reference showing what happens if you design a manually a reward function for this task, just to give you some idea of what this behavior looks like. So here is a, oh, I think my videos are unfortunately a little messed up. Let's see if this will work. Let's see. Okay, so this will be a little out of order, but that's okay. All right, so here the user is showing a demonstration to the robot, and the demonstration here is provided with kinesthetic teaching, which is just a fancy way of saying you hold the robot's arm and you move it to provide the demonstration. And the robot is recording the states and actions. This is the hand-designed reward function, and it's a little aggressive and doesn't always get it in the right slot. This is the learned reward function, I believe. And here it's showing different goal positions. And you can see kind of carefully inserts the plate into the location. This is a demonstration for the pouring task. So here again, the user is showing the robot how to pour into a cup. And the robot is not told where the cup is. It's just showing like, here's the motion that you can use. And it has some visual features that it gets from its camera. And then these demonstrations combined with the autonomous learning can be used to figure out how to pour the almonds. So this is the method that just gets a hand-designed sampling distribution. So this is the one that's not adaptive. And there you can see that it gets the general flavor of the task, but misses the cup. And this is if you actually do the adaptive thing where you adapt both the policy and the reward function. It doesn't succeed every single time, but it generally does reasonably well. Now, one of the, okay, so these are all, I think I already showed all of these. One of the interesting things about this method is that the reward function that's actually obtained in these very high-dimensional problems sometimes is actually not a very good reward function for then re-optimizing the behavior in a new setting, but the policy that's obtained is often a very good policy. And this is a little bit perplexing because, if the whole point of inverse reinforcement learning is to acquire a good, effective reward function, it seems a little weird that you get a good policy but a bad reward function. One of the things that can elucidate a little bit what's going on here is to study an interesting connection between inverse reinforcement learning and something called generative adversarial networks. So I'll discuss this in the remaining part of the lecture, and first I'll introduce how generative adversarial networks work, and then I'll explain the connection between generative adversarial networks and inverse reinforcement learning. So those of you that haven't heard about generative adversarial networks, or GANs, the very brief overview is that GANs are neural networks that are typically used to generate things like images or videos. And they're trained in some examples of applications, for example, this is what's called a conditional GAN. So it's a neural network that's actually looking at this video of a horse and turning it into a video of a zebra, conditioned on a picture of the horse. These are non-conditioned generation, so these are just raw samples from a GAN model that was trained to generate pictures of faces. And this is another conditional GAN example that uses a line drawing as input and tries to make that line drawing look like an actual picture of a cat. And the way that GANs work is that they consist of two neural networks, a generator neural network and a discriminator neural network. The discriminator takes in a picture and tries to predict whether that picture came from the data or from the generator. And the generator tries to output pictures that fool the discriminator into thinking that its output actually came from the data. And now you might immediately think that, well, this sounds a little bit like IRL. So in IRL, you have this policy that's trying to optimize the reward function, and the reward function is trying to maximize the reward in the data and minimize the reward from the policy. And in fact, this connection can be made formal. So in inverse RL, you have trajectories. in generative adversarial networks, you have samples like images. So these are kind of the same thing. That's your data. It's either a trajectory or an image. The policy in inverse RL, this policy that you're optimizing in the inner loop, corresponds to the generator in GAN. So that's the thing that actually produces your trajectory or your image. And the reward actually plays the role of the discriminator. In fact, you can actually formulate inverse reinforcement learning exactly as a GAN for a particular choice of discriminator that depends on the reward. And here's how we can do that. So what we do is we first note that the form for a Bayes optimal discriminator, if you want to figure out that something came from P and not from Q, is this. So if you have a sample and you want to figure out, did it come from P, the optimal discriminator is to do P of tau divided by P of tau plus Q of tau, where P of tau is your data distribution and Q of tau is your policy. And in inverse reinforcement learning, what we're actually doing is we're doing GANs where the discriminator has this form, where we're assuming that 1 over z times the exponential of the reward is the probability of the data. And if you just take this discriminator and you optimize it with respect to psi, that actually gives you exactly the same objective as IRL. So the loss of the discriminator is to make the samples from the data, from P, be classified as samples from the data, and make samples from your policy, from Q, be classified as samples from your policy. And if you parameterize your discriminator in this way, and you plug this into this loss, you actually end up getting the IRL objective for optimizing the reward. And then for the policy, in GANs, the way that you train your generator is to fool the discriminator. And it turns out that if you plug in the discriminator from the previous slide, you actually end up, this is a loss that is minimized, so you maximize your reward. And this log Q term gives you the entropy. So you actually end up with exactly the maximum entropy forward RL problem if you plug in the discriminator from the previous slide into the standard GAN generator objective, which is trying to fool the discriminator. So this gets you this entropy regularized RL or softly optimal RL from last week. So if you have unknown dynamics and you use this approach where you alternate between updating the policy to maximize the reward and updating the reward to try to push up the reward of the data and push down the reward of the policy samples, you're actually exactly implementing a GAN with a particular form for the discriminator. OK, so this is that's what I just talked about. So this guided cost learning algorithm is an instance of a GAN, where the policy is the generator and the reward determines the discriminator. Now, right, so the reward of the samples from the policy is maximized, or the reward of the samples from the policy is minimized, and the reward of the human demonstrations is maximized. There's another algorithm that was actually proposed subsequent to this that takes the GAN connection even further by saying that, well, OK, we don't actually have to represent the discriminator with this funny form, with this funny odds ratio, with the reward in there. We can just directly learn a regular good old-fashioned discriminator as a classifier. So this is a paper called Generative Adversarial Imitation Learning by Ho and Ehrman. And what they did is they said, OK, we're going to have samples from our policy, samples from the human. And now, instead of actually training a reward function, let's just do the standard GAN thing. Let's just train a classifier directly to label these samples as false and these samples as true. And it turns out that you can still do this, and all you have to do is use the log probability of the trajectory being real as your reward function. And you can plug that into your learning algorithm also. Now, and in fact, this particular algorithm has been used in a number of different applications. This is some examples of actually using a sort of a clustering variant of this that can learn different motion styles from demonstrations. So it sort of figures out that the humanoid has different potential styles for running forward and backward. And this is an example video where they actually used motion capture of humans to try to learn a reward function to then re-optimize a policy with a policy gradient algorithm, again, using a variant of this approach. The two methods are basically the same thing, with the difference that here you don't learn an explicit reward function, you just learn the classifier, and then you use the log D as the reward for your policy. So here the discriminator has a particular form, which means that you actually recover a reward and use this as a discriminator. And here, the discriminator is just some classifier. But other than this, both methods are actually a variant of a generative adversarial network. All right, does anybody have any questions about the connection between GANs and IRL? Okay. This is some more videos. So these are more videos from that the second paper, the one that used human motion capture. So they also did some walking motions, some standing up motions, and things like that. So these are all built by taking motion capture data, using that as demonstrations, and then using this the generative adversarial imitation learning algorithm to build the discriminator. Now, one interesting connection that also follows from this from all this work is that inverse reinforcement learning now, okay, we saw that it's equivalent to generative adversarial networks. Inverse reinforcement learning is also equivalent to an energy-based model, and we saw this last week when we talked about the energy-based reinforcement learning. So the Maxent model is a special case of something called an energy-based model, and what that means is that where the reward is the energy, and what that means is that GANs, of course, also optimize energy-based models, of which inverse reinforcement learning is a special case. There's actually been quite a bit of work on combining GANs and energy-based models, and this connection can also be used to derive another formulation of an energy-based GAN, and that's something that's covered in this paper here. So GANs are energy-based models, and IRL is an energy-based model. All right, so to review what we covered today, inverse reinforcement learning refers to inferring unknown reward functions from expert demonstrations. Maxent inverse reinforcement learning infers the reward function by learning under the control as inference framework, which serves to address the under-specification problem, so it disambiguates the demonstrations, and it also addresses the issue that the human demonstrations might be suboptimal, so it actually provides a model of suboptimality. Maxent IRL can be implemented with dynamic programming by exactly computing the forward and backward messages, which is simple and efficient, but it only really works on relatively small, discrete state spaces and known dynamics. I didn't actually cover differential Maxent IRL, but I can provide a citation to that later. I covered sampling-based Maxent IRL, which generates samples to estimate the partition function and can be implemented in large spaces and with unknown dynamics if you want to use a model-free RL algorithm. So I described the guided cost learning algorithm and connections to generative adversarial networks and generative adversarial imitation learning, which is not an IRL algorithm per se because it doesn't recover a reward function, but it can be used to solve many of the same problems. Okay, some suggested readings if you want to learn more about inverse reinforcement learning. So there are a few kind of foundational papers, and I alluded to these earlier in the lecture. So if you want to learn about some of the margin-based IRL, that's the first paper by Biel and Ng. And the second paper by Ziebart et al. Describes the dynamic programming version of the Maxent IRL method. And actually, if you want more background on the theory behind Maxent IRL, I also highly recommend checking out Brian Ziebart's PhD thesis, which you can find on his website. Some more recent papers, so these are all the ones that I covered actually in this lecture. So the guided cost learning, that's the paper with the robot. Wolfmeyer et al., this is the paper that I covered before the break that used deep neural network reward functions with tabular state spaces. And Ho and Ehrman, this is the paper on generative adversarial imitation learning that doesn't directly get a reward function, but just directly learns the classifier. So if you want to learn more, check these out. Remember to submit your final project proposal tonight, and I'll see you all on Wednesday.
For that robot paper, how many samples, how many trial, like I guess,
so that one was trained with guided policy search. I believe it was on the order of 20 to 30 iterations, and each iteration is about 5 samples.
So 20 iterations, oh.
So about 100 to 150 samples.
Okay.
So when we are defining our states, so our actions might not, so like some states might be stochastic and we cannot change the state. It can be like underlying distribution or something, and